Hello, my name is Samuel Carton. I am a postdoc at the University of Colorado Boulder. This is a presentation of my paper Evaluating and Characterizing Human Rationales, which is joint work with Anirudh Rathore and Chen-Hao Tan. So this is a paper about rationales, which, as many of the people watching this presentation will know, are subsets of tokens taken to explain or justify the label in a text classification setting. In this particular example, drawn from the EMNLP dataset, the hypothesis is a contradiction of the premise, a fact which can be explained by the use of the word sits in the premise versus laying in the hypothesis. And then, of course, in this case, a strong model would assign the contradiction class a high probability. Rationales are an explainable AI technique for text, and we are interested in them for the same reasons that we're generally interested in explainable AI, which include enabling human-AI collaboration, ensuring model accountability, making debugging models easier, and discovering new knowledge. Now, given a model trained to rationalize its decisions, a very important question is, how do we evaluate the generated rationales? The most common ways of doing this are 1, comparing them to gold standard human rationales, and 2, automated metrics which don't use any kind of external standard. Among the latter type, a prominent recently proposed metric is Fidelity, which is divided into the submetrics of sufficiency and comprehensiveness, aka necessity. Sufficiency measures whether the rationale alone is sufficient to allow the model to make the same prediction as it did with full information. If this particular rationale that we're looking at here were highly sufficient, then the model would, on the strength of these two words alone, assign a similar probability to the contradiction class as to what it did with the full information, which was 0.96 in our hypothetical example. By contrast, comprehensiveness measures whether the rationale is necessary for making the same prediction by examining the model's prediction on the complement of the rationale, that is to say, without the tokens in the rationale. In our example, if our two-word rationale is highly comprehensive, then trying to make a prediction without those two words should lead to a very dissimilar predicted class probability, possibly even a different predicted class as the model did with the full information. So we have these two types of evaluation, but to the best of our knowledge, the question has not been answered of, what about the fidelity of human rationales? Do human rationales actually show optimal properties when they're evaluated by these automated metrics? And this is an important question because if there is a serious misalignment between these two types of evaluation, then it has to be resolved before we as a community can arrive at consistent standards for rationale quality. In addition to evaluating the fidelity of human rationales, we also propose extensions to the fidelity metrics themselves. We propose a normalization procedure to account for baseline model behavior, and we investigate the relationship between fidelity and model accuracy. Finally, we propose a method for investigating fine-grained rationale properties by drawing so-called fidelity curves based on random occlusion of rationale tokens. We work with 6 datasets for which human rationales are available, 3 single text classification style tasks, and 3 document query reading comprehension style tasks. These datasets vary across a number of dimensions, from rationale to text ratio, as shown in the plot, to various other qualities that are shown in this table that I'm not going to elaborate on. In technical terms, we define sufficiency and comprehensiveness as a difference in predicted class probability between the model operating on full information versus only the rationale or only the rationale complement in the case of comprehensiveness. There's a lot of content on this slide, but the idea is very simple. Given the rationale or its complement, we run the model on the reduced text and then subtract the resultant class probability from the original class probability for that example. In terms of notation, alpha here represents the rationale as a binary mask applied to the tokens of the example X. And that brings us to the main result of the study. We investigate the fidelity of human rationales using 4 models, logistic regression, random forest, LSTM, and the Roberta variant of BERT. Looking at model accuracy, we see basically what we would expect. Roberta outperforms all the other models, and LSTM outperforms the non-neural models in almost every case. Looking at sufficiency, we see that the sufficiency of human rationales is generally between 0.8 and 0.95, with the same rationales showing higher sufficiency on weaker models generally than on stronger ones. And finally, comprehensiveness is an interesting case because it's kind of difficult to interpret. We find that human rationales are more comprehensive for the stronger models, but it's difficult to otherwise interpret these numbers, which are on seemingly a completely different scale from sufficiency. What comprises good comprehensiveness, really? What is the target number here? In a moment, I'm going to talk about how we can use normalization to at least partially answer some of these questions. For most of the rest of this talk, I focus primarily on Roberta, as it generally represents the state-of-the-art in NLP. Breaking down rationale fidelity scores by class gives us a little additional perspective on what's going on here. EMNLP displays a class asymmetry and sufficiency, with contradiction rationales proving more sufficient than for the other two classes. And comprehensiveness varies wildly between classes for both WikiAttack and, to a lesser extent, Movie, Multi-RC, and Fever. In addition to the interpretation issue I mentioned a moment ago, there's also a question here of, are these disparities because rationales are intrinsically more comprehensive for one class versus another, or because we're learning very biased models, which tend to lean strongly toward one class in the absence of available information? This is another question that we can answer with normalization. So to mitigate these issues of interpretability and model bias correction, we propose the idea of normalizing fidelity scores relative to baseline model behavior. We do this by defining a quote-unquote null difference, which is the difference between model output between full information and no information at all. This null difference can be thought of as the sufficiency of an empty rationale or the comprehensiveness of an all-inclusive rationale. We define these ideas as extensions of the definition of sufficiency and comprehensiveness. As you can see from the equations at the bottom of this slide, the basic idea is very simple. We calculate the null difference, and then we divide the sufficiency and comprehensiveness by it to generate properly normalized values. And this is the result. We can see that the high sufficiency of the weaker models was an artifact of model uncertainty, and that really the human rationales are not much more sufficient than empty rationales for these models. We can also see that comprehensiveness has been projected closer to the same scale as sufficiency, although rationales still fall short in comprehensiveness compared to sufficiency even under this normalization regime. Performing the same transformation on the class-wise results for Roberta, we see that the skewed results for Fever do indeed seem to have been the result of model bias, but there are genuine discrepancies present for WikiAttack, Movie, and Multi-RC. We also find that there are discrepancies in sufficiency for WikiAttack that were actually masked by the lack of normalization. A major sticking point in interpreting fidelity scores is the question of their practical implication. Does a low sufficiency score really matter, or does it just mean that the classifier is less confident about the correct class? And how does it affect matters when the model is allowed to adapt to the presence of rationales, as in the case for rationale architectures? In this plot, we investigate the accuracy of the Roberta model when trained and evaluated on full information versus trained on full and evaluated only on rationales, as well as when it is both trained and evaluated on rationales. This is a visual illustration of what I mean. You can see in the three different conditions, the full information is either used or not used during training, and either used or not used during evaluation. What we see is kind of interesting. Evaluating on reduced data hurts in 3 out of 6 cases, but it actually helps in the other 3. Moreover, in 3 cases, allowing the model to adapt to the reduced data actually improves the performance over the full information case. So what this all tells us is that the suboptimal sufficiency can be associated with either higher or lower prediction accuracy, giving us another reason to be careful about our interpretation of these fidelity metrics. Finally, there's a whole set of qualities that rationales can hold which are not really captured by existing fidelity metrics. One such quality is token redundancy, where the rationale contains more tokens than are necessary to predict the correct class. Another such quality is token irrelevancy, where the rationale contains tokens that are irrelevant to the task at hand. Tokens can be dependent on one another, allowing for correct prediction if and only if they are both present. Or they can be independent and contain predictive signal all by themselves. In order to evaluate these qualities, we propose to examine how sufficiency and comprehensiveness degrade as tokens are randomly removed from the human rationales. Depending on the various levels of redundancy, irrelevance, dependency, and independency, we expect to see different rates of degradation in sufficiency and comprehensiveness. Briefly, an example here is the movies dataset in orange, which shows a very slow drop in sufficiency and a relatively fast drop in comprehensiveness, indicating that it has many redundant tokens. So that was a lot of information in a relatively short talk. We analyzed the fidelity of human rationales, and we proposed extensions to the basic fidelity metrics, including normalization, accuracy analysis, and random occlusion of tokens. The main takeaways from our study are that human rationales are not necessarily optimal, and that model properties have a big impact on rationale fidelity assessments, and that fidelity itself is not necessarily correlated with accuracy. What this all points to is that the interpretability community really needs to be careful in setting benchmarks for rationale quality. For example, while the normalization scheme we propose may not be the one the community settles on, we suspect that some kind of normalization is necessary moving forward to evaluate the fidelity of explanations across different models and data sets. And that concludes my talk. I really appreciate anyone who stuck around this long, and I welcome questions or further discussion. Thank you.